Okay, AP Calculus kids. We're going to take a look at two tests today. The first one is the P-series. Okay. Number one, what is a P-series? Okay, it's a series of the form sigma n equals 1 to infinity 1 over the constant number to the p. Okay, so this would equal 1 over 1 to the p plus 1 over 2 to the p, 1 over 3 to the p, yada, 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 plus 1 over n to the p plus dot, 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 is called a P-series. Where P is a positive constant. Okay, and when P equals 1, you have the series 1 over n. Okay, this is a famous series. When it's indexed starting at 1, you have to pay attention to that. This is 1 plus a half, plus a third, plus a fourth, yada, yada, yada. And it's called the harmonic series. Which diverges. So if you ever have the series, you're allowed to just say it diverges because it's the harmonic series. Okay, so let's look at the P-series test. Okay, so 1. If P equals 1 or is less than 1, either or, the series diverges. Okay, 2. If P is greater than 1, the series converges. Okay, what it converges to, we don't know. Okay, so we can't find its sum. All right, so let's take a look. Okay, example, sigma n equals 1 to infinity of 1 over n times the cube root of n. All right, for some reason when I first made this video, I don't know why the recording didn't save on this page. But anyway, for example 2, you have the series n equals 1 to infinity of n over the cube root of n. So you put the n in the denominator. N to the negative 1 times n to the 1/3 is n to the negative 2/3. So the p-value is negative 2/3 because you have to have it in the denominator, is less than or equal to 1. Therefore, the series n equals 1 to infinity of b sub n, I just named the series b sub n, diverges by the P-series test. Okay, in example 3, we have the series n equals 2 to infinity, because it can start anywhere. The bottom index doesn't matter, guys. So, then we have the cube root of n over n. So I put the cube root in the denominator, so it becomes n to the negative 1/3. I use product of powers, and I get n to the 2/3 in the denominator. 2/3 is less than or equal to 1. Therefore, the series c sub n from n equals 2 to infinity diverges by the P-series test. Okay, so we're going to look at the integral test. Okay, the to use the integral test, a function f has to be continuous, positive, and decreasing. You can remember that by co-poti. You'll hear me saying that in class. For x is greater than or equal to 1, and a sub n, we're going to let a sub n equal f of x. Then the series n equals 1 to infinity of a sub n, and the integral from 1 to infinity of f of x dx either both converge or diverge. Okay, the integral's integrand is a continuous function, and series are discrete functions. So I'm going to prove the integral test here. So on the left, I have the series. I'm showing that the series from 2 to 5 of f of x is less than the integral from 1 to 5 of f of x. Because when you have a right Riemann sum, remember, a right Riemann sum, you have a decreasing, f of x is decreasing, a right Riemann sum is going to be an underestimate. Okay, and then on the right, I have left Riemann sums. So you can see that they're overestimates. Okay, so when f of x is decreasing, LRAM is an overestimate. Okay, so that gives me this rule 2 that sigma x equals 1 to 5 of f of x is greater than the integral from 1 to 5 of f of x. Okay, so now I'm going to add a 1 to both sides of equation 1. And I end up with the bottom index changing from a 2 to a 1. So the series f of x from x equals 1 to infinity is less than a sub 1 plus the integral from 1 to 5 of f of x dx. Now you put these two equations together, and we have the integral from 1 to 5 of f of x dx is less than the series from 1 to 5 of f of x, which is less than a sub 1, which is a finite number, plus the integral from 1 to 5 of f of x dx. So when that's the case, okay, think about it. Okay, if the integral is convergent, well then this series would have to be convergent because it's less than it, right? If the integral is divergent, this would already diverge, and the series is greater than that, so it would have to diverge. So they walk hand in hand. All right, let's take a look at an example. We have the series from 1 to infinity of n over n squared plus 5. So f of x is going to be x over x squared plus 5, okay, which is continuous, positive, and decreasing, okay, when x is greater than or equal to 1, right? So we're going to look at the integral from 1 to infinity of x over x squared plus 5 dx. Now you already know how to do this. That becomes the limit as a goes to infinity of the integral from 1 to a of x over x squared plus 1. I did my u sub over here. Okay, so you can just check that out. So I end up with half ln of x squared plus 1 from 1 to a. Substitute those in, but as the limit is a goes to infinity of ln of a squared plus 1 is infinity, So therefore it diverges, right? So how would you write this explanation on an AP exam on a free response? You would have to say, all right, f of x equals x over x to the fifth plus 5 is continuous, positive, and decreasing. You can remember that again by co-pody, continuous, positive, and decreasing. And the integral of f of x diverges. The series diverges by the integral test. Okay, so that's very important, and we're going to continue that in class tomorrow. All right, thanks, kids. Okay, so that is how that test works. We'll do one more example. Example 3. Okay, the cube root of n over n. So we have n to the 1/3 divided by n to the first. So that is going to be n to the negative 2/3, right? All right, well, the series is 1 over n, so it's going to be 1 over n to the 2/3. Okay, because remember, you need to have it in the denominator, right? So if you look at the previous page,